The level of water in a cone of radius 8 centimeters and height of 20 centimeters. So I've drawn the cone over here to the left. The height is increasing at a rate of 1 centimeter per minute. So the height is increasing here. And at the time when the height is 12 centimeter, we want to know the rate at which the volume is increasing in the cone at that point. Okay, so first of all, we need to make sure that we have the relationship with the parts that are important here. So we need to connect volume, height, radius together, and we can do that through the volume of the cone formula, which I've written here. The volume of the cone is the area of the circle times the height. That gives us a cylinder, and anything that comes to the tip, we're going to multiply by 1/3. Now, what's key here is it's going to be easier to do this with just one variable. Instead of having R and H, we're just going to get rid of one of these variables to have it in terms of one variable. In this case, the problem is relating to height. So we're just going to get rid of the radius and do this as a problem based on height. And we can do that because the ratio of the radius to the height remains the same throughout that cone because of that similar triangle relationship. So I'm going to use that radius and then that relationship, and I'm going to solve for height. So I end up with, in this case, it simplifies to 2/5h. And what I can do is instead of using the height, or so the radius, I'm going to replace the radius with this expression for height. And that way, I'll have an equation that's based on just height, and then it'll be easier to differentiate. Now, I will also do a separate solution where we can actually use our implicit differentiation, and we can actually involve the height, and I'll show you a different solution for that. So for now, we're going to simplify things, and we're just going to make this into volume is equal to 1/3 pi, and instead of r squared, we're going to replace that r squared. We're going to replace that with 2/5h. And so this now becomes a function of h, and we end up simplifying this. We end up with 4/75 pi h squared, and h becomes h cubed. Okay, so that 75 comes from the 5 squared times 3. I've got a pi in there as well. Okay, so I now have my volume formula. I'm going to differentiate this with respect to time because I have a rate going on here. I have a rate of 1 centimeter per minute. And just going to write that over here. That 1 centimeter per minute, that is the change in height over the change in time. I don't have a time variable in my formula, but I can introduce it with the chain rule. So I'm going to find dV by dt. Okay, that's what I'm looking for. The rate at which the volume is increasing. Okay, that's going to be this piece here. I want to know the rate at the volume is increasing. So I'm going to differentiate that with respect to time. Differentiating this, I'm going to end up with 12 pi over 75. Okay, multiply by using the power rule, and then times 3, and then reduce the power by 1. But because I differentiate, this is dV by dH, okay? I still need to apply the chain rule, so dH by dt. Okay, and this will, if I multiply this together, I definitely get my dV by dt, and I've generated two things here, my dV by dt, which I'm solving for, but I've also generated dH by dt, which I have been given. So at this point then, I just need to, once I've differentiated, I just need to plug in the parts I know and solve for the parts I don't know. So what do I know? Well, I don't know dV by dt. That's what I'm trying to solve for. I have 12 pi over 75. The h is known because I was told that the h was 12 centimeters. Okay, the height at present is 12 centimeters, so I'm going to plug that in for my h. So 12 centimeters. And the h by dt, I've been told as well, it's going to be 1 centimeter per minute. Okay, so the only thing that I need to solve for then is the dv by dt, and that's what I'm looking for. So I just need to, in this case, I don't need to solve for anything, I just need to calculate this. I'm going to basically end up with 17 cubed, and 17 cubed is 1728 pi, 12 cubed is 1728 times pi divided by 75. This actually simplifies, but this is going to be, now the units is going to be centimeters squared times centimeters, with centimeters cubed, and per minute. And that is the right rate that I want. That is a change in volume over change in time. When I work this out on my calculator, it works out to be the 72.38 centimeters cubed per minute. And that's the rate that I wanted. Okay, and if we look at that, go back to the animation, this is the same rate that we had calculated at that specific time.